Watch this. What just happened? The answer to that question explains how water turns to vapor, how opinions spread on social media, how neurons fire in the brain, how to make the best cup of coffee, and why fluids do this.
All fluid flow is governed by a set of equations called the Navier-Stokes equations. Think of them as Newton's second law as applied to the movement of a massive fluid. But the problem is, we can only solve the Navier-Stokes equations for a small number of special cases. For example, we can write down an equation that describes how fluid moves slowly through a long straight pipe. If the fluid is moving much faster, however, the flow becomes turbulent and we no longer have an exact solution.
In this module, we will be talking about the theory of far from equilibrium self-organization. We will firstly discuss the concepts of order and randomness in terms of symmetry and information theory. We will then talk about complexity as the product of an in-between or phase transition state. And finally, we'll discuss the term edge of chaos and talk about how self-organization is thought to be dependent upon noise and random fluctuations in order to stay generating variety. Far from equilibrium self-organization is a model that describes the process of self-organization as taking place at a critical phase transition space between order and chaos when the system is far from its equilibrium. But let's start by talking about organization. Organization is an ordered structure to the arrangement of elements within a system that enables them to function. As such, we can loosely equate it to the concept of order. Both order and organization are highly abstract concepts, neither of which are well defined within the language of mathematics and science, but probably the most powerful method we have for formalizing them is through the theory of symmetry. The theory of symmetry within mathematics is an ancient area of interest, originally coming from classical geometry, but within modern mathematics and physics, it has been abstracted to the concept of invariance. In this way, symmetry describes how two things are the same under some transformation. So, if we have two coins, one showing heads and the other tails, by simply flipping one of the coins over, it will come to have the same state as the other. Thus, we don't need two pieces of information to describe the states within this system. We can describe this system in terms of just one state and a flipping transformation that when we perform it will give us the other state. Now, say instead of having two coins, we had an apple and an orange. Well, there is no transformation we know of that can map an apple to an orange. They are different things. There is no trivial symmetry or order between them, and thus, we need at least two distinct pieces of information to describe this system. This second system requires more bits of information to describe its state. Thus, we can say it has a higher statistical entropy. The point to take away here is that we can talk about and quantify order and randomness in terms of information theory. That ordered systems can be described in terms of these transformations, which we encode in equations. Ordered systems are governed by equations, whereas random systems are not. But because there is no correlation between the elements' states in these random systems, they are governed by probability theory, the branch of mathematics that analyzes random phenomena. Complex systems are by any definition nonlinear. Complexity is always a product of an irreducible interaction or interplay between two or more things. If we can just do away with this core dynamic and interplay, then we simply have a linear system. If the system is homogeneous and everything can be reduced to one level, then it might be a complicated system, but it is certainly not a complex system. Thus, one of the main ideas or findings of complexity theory is that complexity is found at what is sometimes called the interesting in-between. If we take some parameter to a system, say its rate of change or its degree of diversity, and turn this parameter fully up, what we often get is randomness or continuous change without any pattern. Or if we turn it fully down, we get complete stasis or homogeneity with very stable and simple patterns. It is often the case that with too much order, the system becomes governed by a simple set of symmetries. Too much disorder results in randomness, and the system becomes subject to statistical irregularities. It is only in between that we get complexity. On either side of this, there is a single dominant regime or attractor that will come to govern the system's behavior. It is only when a system is far from its equilibrium, away from one of these stable attractor regimes, that we get a phase transition area representing the interplay between the two regimes. In this space, the system is much more sensitive to small fluctuations that can take it into either basin of attraction. This phase transition area is also called the edge of chaos. The phrase edge of chaos was first used to describe a transition phenomenon discovered by computer scientist Christopher Langton. Langton found a small area conducive to producing cellular automata capable of universal computation. At around the same time, physicist James Crutchfield and others used the phrase onset of chaos to describe more or less the same concept. In the sciences in general, the phrase has come to refer to a metaphor that some physical, biological, and social systems operate in a region between order and either complete randomness or chaos, where the complexity is maximal. The edge of chaos concept remains mainly theoretical and somewhat controversial, but it is often posited that self-organization and evolution can only really happen in this phase transition space. There may be a number of different interpretations for why this is so, but one way of understanding it is that self-organization requires entropy and evolution requires variety. Unlike external intervention, where we can take a well-ordered system and simply reconfigure it by transferring energy to it from some other external source, in this way we go from one ordered regime to another without the need for entropy to enable the process. We simply need some input of energy. But as we know, self-organization does not happen in this fashion. It is internally generated on the local level, and this process requires the presence of entropy and randomness for elements to be available for reconfiguration into a new regime through feedback loops that originate as weak signals or fluctuations. A number of different researchers have posited different theories around this process of self-organization far from equilibrium. The principle of order from noise was formulated by cybernetician Heinz von Foerster in 1960. It notes that self-organization is facilitated by random perturbations and noise that let the system explore a variety of states in its state space. A similar principle was presented by Ilya Prigogine as order through fluctuations or order out of chaos. Researcher Per Bach also looked at this phenomenon in terms of what he calls self-organizing criticality, the mechanism by which complex systems tend to maintain themselves on this critical edge. Many of these theories talk about both the need for entropy and variety in order for the system to stay adapting and evolving over a prolonged period of time. In summary, we have been talking about the process of self-organization taking place far from equilibrium at an interplay between order and chaos, a theory that may have a lot of conceptual substance to it, but remains a long way from having a proper formalization. We talked about how order and randomness can be described in terms of symmetry and information theory. We looked at complexity as phenomena that arise at the interplay between different entities or regimes. Finally, we discussed the term edge of chaos and the role it is thought to play in the process of self-organization.
Tornadoes occur on every continent, except Antarctica, but more form over the central United States than anywhere else, in a zone called Tornado Alley. That's because conditions in the alley are ideal for creating tornadoes. Warm, humid air, low to the ground, moves north from the Gulf of Mexico and collides with cool, dry air high above the ground rolling in from the Rocky Mountains. The collision of air masses creates a supercell, a massive thunderstorm that has a strong, rotating updraft of air. Scientists aren't exactly sure what happens next, but the leading idea goes like this. The difference in speed between the faster high winds and the slower low winds causes the air in between to rotate around a horizontal axis. If one end of the rolling air gets caught in the updraft, it's bent upward and forms a funnel cloud. Its spin gets tighter and faster, and the cloud gets longer. Rain or hail from the thunderstorm can then push down on the tail of the funnel cloud till it reaches the ground, forming a tornado.
Well, with tornado formation or tornadogenesis, what we're finding and what other people are finding is that you might have a rotational lock, but it's a rather weak rotation. And what's the characteristics of the surface are the important elements that trigger tornadogenesis. That could be topography, that could be variations in surface roughness, or it could just be surface roughness itself. And what we're finding is that circulation, weak circulation might be aloft, but what happens is the formation of the tornado occurs down in the lower several hundred meters of the atmosphere and then builds upwards. So according to that research, tornadoes don't really touch down and lift off. A better terminology would be tornadoes form down at low levels and dissipate at low levels.
This is Doppler on Wheels, or DOW, a rugged mobile radar unit that does its best work in dangerous places.
At the back of the truck is the real action end of the Doppler on wheels, and that's the biggest dish that we can get down the road.
With support from the National Science Foundation, meteorologist Josh Werman and his team at the Center for Severe Weather Research study hurricanes, tornadoes, and blizzards from the inside.
Really, during its first weeks of operation, it revolutionized how we think about observing phenomena of this type. Hurricanes, tornadoes, nighttime convection. But the first time we intercepted a major tornado and got about 2 or 3 kilometers from it, and were able to take slices through that tornado and map out the wind, see the debris cloud, everybody was extremely excited.
When severe weather threatens, team members coordinate a fleet of storm-chasing vehicles from this compact control room inside the Dow. Others are on pod duty.
These are portable, rugged weather stations. And the idea is if a tornado is coming towards us, we drive on a road and drop 24 of them in front of the tornado.
It's 3 kilometers from the Dow right now.
This kind of work is a sure bet to get the adrenaline pumping.
There's a natural tension between being ambitious, trying to get up as close as possible to the storm, and also trying to keep our crew safe. But the balance is always towards safety. This is not a Hollywood movie where if we get this data set, great, but we might die trying.
But the images they capture will blow you away.
By making maps of those winds and seeing exactly which wind gusts knock down this building, we can learn a lot more about what kinds of winds do which kinds of damage.
How is entropy related to probability? Have you ever wondered why things tend to become more disordered over time? This question leads us to a fascinating concept in chemistry known as entropy. Today, we will uncover how entropy relates to probability, a connection that is essential in understanding thermodynamics. Entropy measures the disorder or randomness in a system. To put it simply, it tells us how many different ways we can arrange the particles in a system while still keeping the overall appearance the same. The more ways we can arrange these particles, the higher the entropy. This relationship is crucial in chemistry education and is recognized by the International Union of Pure and Applied Chemistry Standards. Now, let's look at the mathematical side of this. The Boltzmann equation is a key formula that helps us understand this relationship. It states that entropy equals the Boltzmann constant multiplied by the natural logarithm of the number of microstates. In this equation, the term microstates refers to the different arrangements of particles that can exist in a system. When we have a system with many microstates, the entropy is high. For instance, consider a gas in a container. When the gas is confined to a small space, it has fewer possible arrangements, leading to lower entropy. However, when the gas expands into a larger volume, the number of possible arrangements increases dramatically, resulting in higher entropy. This increase in entropy is not just a random occurrence. It reflects the probability of finding the system in a particular state. In thermodynamics, systems naturally evolve toward states that have higher probabilities, which means they tend to move toward higher entropy. This principle is at the heart of the second law of thermodynamics, which tells us that the total entropy of an isolated system will increase over time. To visualize this, think about mixing two different gases in a container. Initially, each gas occupies its own space. As time passes, the gases mix, and the number of ways to arrange the particles increases. This mixing leads to a more probable state with higher entropy. In summary, entropy is fundamentally linked to the probability of how a system can be arranged at the microscopic level. The greater the number of arrangements, the higher the entropy. This relationship helps explain why systems naturally progress toward disorder and equilibrium. Understanding this connection is vital for anyone studying chemistry, as it lays the foundation for many concepts in thermodynamics and chemical behavior.